You don't have to simplify the derivative. Just give me the raw derivative, all right? You can use your notes. It's an open note quiz. Hey, you know that thing you were asking me about? We're only going for like another 3 minutes. Okay, thank you. Yeah, I'll put it in. All right. This is an open note quiz, but you only have like 2 more minutes, so do what you can. Thank you. Thank you. They're over there if you can't see them. Ooh. Thank you. Just one more minute. Okay, thank you. All right, thank you. Okay, I'm calling time, so turn in what you have. Thank you. Anybody else? Last call. All right, thank you. Thank you, thank you. Anybody else? All right. Okay, so the quiz problems. Number 1 was actually number 14 out of the, I gave you a homework assignment, right? I don't think number 14 was in the homework assignment, but that was exactly number 14. And then number 2 was number 22, but I just tweaked it just a little bit. So I'm just going to give you what the answers to these are, the raw derivatives. The answer to number 1 should have been 2x natural log of 2x plus 1 plus 2 over 2x plus 1 times 2x. There's different ways you can do this. This is product rule. Okay, so you have to do the product rule on that first one. And on the second one, you have to do quotient rule. So you do derivative of the top, which is itself, times the bottom. Oops. Times the bottom. Minus the derivative of the bottom. This one is a little tricky. It's itself. Derivative of e to the negative e to the 2x. That's the derivative of the bottom. And then times the top. And then all over the bottom squared. I'm missing a 2. Hold on, I'm missing a 2. E to the 2x squared. I'm missing a 2 right here. E to the x. There we go. That's your answers. All right. I'm not going to go through any more detail on that. If you want to talk to me about those problems after class, we can. So I would expect that you could do both those problems in 9 minutes. I think that's plenty of time to do that. So if this again is just to give you an idea of what my expectation is at this point, right? So we're going to continue today with 3.3. We need to finish the section on logarithms and exponentials, talking specifically about this thing called logarithmic differentiation. Then we're going to cover 3.5. It's going to go really quick through 3.5. We're going to start 3.7. All right? Okay, so the idea of last class is that we now have the ability to take the derivative of exponential and logarithmic functions, right? And then once we did that, we could throw in product rule, quotient rule, chain rule. It's all in play, but we just have these new functions. Logarithmic differentiation is a tool. It's a way that we can take derivatives of things using logarithms to assist us in finding derivatives. So like this example here, we have f of x is this function. Nowhere in here is a logarithm. Nowhere in here is an exponential, right? This is just square root. That's like a polynomial. Polynomials on the bottom. So there's no logs, no exponentials. However, we can use logarithmic differentiation to help us get this derivative. And the thing that's going to let me know that I should probably be thinking about logarithmic differentiation is the fact that I have a bunch of multiplications, division, and a bunch of things being raised to powers. And the logarithm, those properties from last class, the logarithm allows us to split things up, right? If we have a logarithm, which we don't here. So we did one of these problems last class, right? What I'm going to do to start this problem is I'm going to rewrite this as y equals instead of f of x. And then I'm going to change, I'll leave the square root. Leave that there. So I'm just going to, this is just a change in notation there. Are you all comfortable with the idea that if I was really like stubborn, I could try and take this derivative right now, doing quotient rule, and it would just be a mess? Okay, but I'm not going to do that because I see that I've got all these powers and multiplication, division. I'm going to rewrite this with y, and then I'm going to take natural log on both sides of the equation. So when I take natural log on the left side, I get natural log of y. On the right side, I get natural log of this big ugly thing, right? But the whole reason I'm doing that, right? The whole reason I'm doing that is because I'm now going to employ the properties of logs, right? And I have natural log of division first, right? Because I have division, I can split this up. So natural log of y equals natural log of the top minus natural log of the bottom. Is that fair? Yeah? Now what? Everywhere I see multiplication, I can now use the property of logs to split those into two logs with addition between them. So still on the left side, natural log y equals, now this becomes two logs. Natural log of the square root of x, right? I'm going to rewrite the square root of x as x to the half power. Because in the next step, I'm going to pull the power out front, right? Use that other property of logs. So that plus natural log of here, x plus 1 to the fourth. And then we talked last class about how you have to be careful with this minus sign. Because if this splits into two pieces, the minus sign must distribute to both, right? And I think last class, you all told me just go ahead and distribute it, right? So I'm going to go ahead and do that now. I'm going to have, this is going to be natural log of x minus 2 to the third. I'll have a minus in front of it. And then this one, when it split, would have been a plus, but now the minus comes through. So another natural log, x plus 5 to the 7. Any questions there? Next thing, pull all the powers out, right? Pull all the powers out front. So natural log y equals 1/2 natural log x. I don't really need the parentheses anymore. Plus 4 natural log x plus 1 minus the 3 comes out, natural log of x minus 2 minus the 7 comes out, natural log x plus 5. There we go. We have expanded this expression, right? We have expanded this expression using the properties of logarithms. Now you can take the derivative. And we're going to do implicit differentiation, which means we're going to take the derivative on both sides of the equation with respect to x. All right, so when you take the derivative of the left side, right, at this point, when you take, I want everyone to understand, this is the point I'm going to take the derivative, right? So from here to here, what's the derivative of the left side? What's the derivative of natural log of something?
1 over it.
1 over it, right? So 1 over y. Let me put it over here. But don't forget, you have chain rule, right? You have chain rule? So it'll be 1 over y, what? dy dx. So the left side is 1 over y times the derivative of y with respect to x. So derivative natural log of something is 1 over the something times the derivative of what's here. Derivative of what's there is dy dx. All right, equals, now the 1/2 comes for the ride. Derivative of natural log of x would just be 1 over x. So equals 1/2 times 1 over x. Okay, I keep going, right? Plus 4 times, what's the derivative of natural log of x plus 1? 1 over x plus 1. And then minus 3 times 1 over x minus 2. And finally, minus 7 times 1 over x plus 5. The one thing I would be careful with, okay, and I didn't give it to you on this example, I should have. What if there would have been a number in front of this? Like let's say this right here, instead of natural log of x plus 5, what if it was natural log of 3x plus 5? Then when I take derivative of this, I would get 1 over 3x plus 5, right, times 3. Because you would have chain rule. You'd have to go back and take the derivative of what's inside of here, and you would get a 3. The reason we didn't have to worry about that with everything we did is because, like here, when I take derivative of natural log of this, it's 1 over that, right? But then derivative of what's in here is just 1. And that happened for all of these. The derivative of that's just 1. Make sense? Okay, just be careful, all right? All right, are we done? Is this our answer? Well, what are we trying to find? The derivative, right? dy dx? I need it by itself, so I need to get rid of y over here. So multiply both sides by y. You'll do this on every logarithmic differentiation problem. You'll always have 1 over y dy dx on the left side. You'll always have to multiply by y on both sides. So here it goes away. I have to multiply the entire right side by y, right? And now you go back, I erased it. What was y? That's what I started the problem with, right? Didn't we write down what y was? So instead of writing y here to save myself time, oh wait, it was right there. I just erased it. Right there. It was right there. That's y, right there. Right? That's y. So I need to slap onto this square root of x, x plus 1 to the 4th over x minus 2 to the 3rd, x plus 5 to the 7th. That's your derivative. It ain't pretty, but that's what it is, okay? I mean, like technically, you would need to distribute that through. Boom, 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 boom. But we're just going to leave it like this. Questions? Okay, so on your homework, problems 51 through 54. 51 through 54 are problems of this sort, all right? And in the homework, it says use logarithmic differentiation to find the derivative, right? It tells you what it wants you to do. On your exam, I will not tell you use logarithmic differentiation. I'm just going to give you a function, say take the derivative. So you have to recognize that this is best suited for logarithmic differentiation. Understand? I think it's obvious. Because when you look at that, you do not want to take derivative of this using like traditional rules, right? So you do a little bit of work first. It's a little easier to take this derivative, right? Okay, we're moving on. So I have a question for you now. I'm going to give you two functions here, and I'm going to ask you for their derivatives, all right? So I want you to look at y equals x to the 3rd versus y equals 3 to the x. I want to know the derivatives of these. Okay? So what's the derivative? And we're assuming we're taking derivative with respect to x. Okay, so good old-fashioned derivative. So what would y prime be here? 3x squared, right? This is not a trick question. The derivative of that, right, is 3x squared. We've known this for weeks and weeks and weeks. This one we just talked about last class, right? This is different, right? The derivative of this is what? Itself times natural log of 3. That's a formula we established last class, right? All right, so they're different, right? The main difference between these two expressions, this one is a power function, right? It is x raised to a power. And this one is an exponential function, which is a number, right? A constant raised to the variable, right? The variable's in the exponent here. The variable here is in the base. They're different, right? So what do you think about this then? Versus y equals x to the x. What's its derivative? Well, we have a little bit of a problem here, don't we? Like, it's not this, right? Because this needs to have a number up here, right? So it's not this, but it's not this either because this has to have a number on the base.
It'll be done as composition.
Pardon?
It'll be done as composition.
Well, that is, it's x raised to the x. So you can think about its composition, but what rule are you going to use? Like, do you use this rule? Do you bring the power out front? You see what I'm saying? Like, do you do this? So I guess what I'm getting at is there's kind of two perspectives you can have right now. You can think maybe, right? Maybe it's this. Bring the power out front, and then x to take one away from the power. That's the power rule, right? That's me doing the power rule. I wonder if that's right. Okay, or maybe, how about this? Let's try it using this rule. What would, if I use this rule, what would it be? Itself, right, times natural log of x. You see that? They're both wrong, okay? These are both wrong because in order to use this rule, that has to be a constant. It has to be a number, it has to be bigger than 0, and it can't be 1. And over here, this has to be a number, can't be a variable. So this is the first time that we've ever seen this. And actually, if you go back and think about all the math you've done up to this point in your life, I'm pretty sure you've never dealt with a function that looks like this, where you have this right here is some function of x, right? And this right here, the exponent, is some other function of x. Now I'm going to call it g of x. Even though these are the same function, it doesn't have to be. I can give you another example. Like, what about this? What if I give you y equals, how about sine x raised to the sine x? We've never, let's not use sine twice. It doesn't have, I don't want you to think it has to be the same. There we go. Sine x to the cosine x. What's the derivative of that? Well, we have to first believe that these actually have graphs, right? Because derivatives are slopes of tangent lines. So let me go to Desmos. Let me graph this so you believe that this actually does have a graph. Here's x raised to the x. Wait, hey, weren't we talking about this after class? Yeah. Do you see it's showing the dots now? What the hell's going on with this thing? All right. So do y'all agree that there looks like there is a graph to that, x to the x? Yeah, y'all see it, right? There's some, oh wait, when I zoom in, uh-oh, it went away, it freaked out. Okay, so there we go. We have some graph, at least for positive values of x, right? All right, and then what about if I try the other one? What if I do sine x raised to the cosine x? Hey, there is a graph, right? There's a graph, so I should be able to find slopes of tangent lines, right? So how do we do it, right? How do we do it? How do we do this when we have some function of x here raised to some other function of x there, right? That's the general format of what we're seeing here, right? What we're going to do is logarithmic differentiation. Exactly what we were just doing. So let's do this one first. All right, I'm going to do this one. So on the previous example, what told you to use logarithmic differentiation? What indicates that? Powers and products and quotient, division, right? That's what kind of said, logarithmic differentiation. Here, what tells us logarithmic differentiation is a function of x to a function of x. A function of x to a function of x. That's what tips you off, okay? So I'm going to start the problem here by first taking the log on both sides. Natural log of y equals natural log of x to the x. Right? That's where I'm going to start. And then I'm going to use the property of logs on the right-hand side, and I'm going to take this power and I'm going to drop it down in front. So I'm going to have natural log y equals x times natural log x. And now I'm going to do my implicit differentiation. So I'm going to take the derivative now. The derivative of the left side, 1 over y dy dx. We've done that now 3 times. And the right side, how are you going to take the derivative over here? Product rule. That's just a good old product rule, right? It's the derivative of the first one times the second one plus what's derivative of the second one? What's derivative of natural log of x? 1 over x times the first one, right? That's what we got. Okay, and then that is, yeah, I'll finish it right here. That is 1 over y times dy dx equals, I'm just cleaning up, that's just natural log of x. And then isn't this just 1? Okay, so plus 1. Almost done. What's the last step? Yeah, multiply both sides by y, right? Get dy dx by itself. So if I multiply both sides, can't talk. Dy dx, if I multiply both sides by y, I get natural log of x plus 1 times y, right? Times y. But what's y? X raised to the x. That's your derivative. Yeah, you could distribute that through here, right? Couldn't you? I'll leave it. That's fine as an answer. I just want to show you. You could rewrite this as like x to the x times natural log x plus x to the x. That's just another way it could look, right? But that's fine. Seem reasonable to do that? Okay. All right, let's do this one. It's going to go the same way. So we have natural log y on both sides, natural log of sine of x, right, raised to the cosine x. I'm going to pop the cosine out to the front of the log, right? Right, without that log, without the logarithm, you can't be popping things out front, right? You're not free to do that with anything, right? You have to have the logarithm there to drop that out. And then, once we're here, we can differentiate, because that, do you see on the right, it's just going to be another product rule. So we have 1 over y dy dx equals, okay, product rule here, so derivative of the first one is negative sine x times the second one, no derivative, plus the derivative of this one, which is 1 over sine x what? What's derivative of natural log of sine x? 1 over sine x times cosine x, right? That's because you have to take derivative of what's inside. And then don't forget we have to finish off the product rule. The first function was cosine again, right? Everyone see that? And then I could clean this up, but really what I'm going to wind up doing is this. I'm going to take this whole thing, right? Multiply both sides by y, and y for us is sine x to the cosine x, and I'll just cancel the y out over here, right? So that's your derivative. dy dx is all of this. I haven't cleaned it up. I'm just leaving it like this. Sine x to the cosine x. Okay, problems number 55 through 60 are like that. I recommend you do all these. I recommend you do them all, just for practice, all right? So this reminds me of something. When I was in school, I waited tables. Can I erase this? Anyone need this? I waited tables. It seemed to be a good job when I was a student because somewhat flexible schedule. And so there was a little whiteboard. Did I tell you all that story about the little whiteboard? Most restaurants have like a whiteboard in the kitchen where they'll say like we're out of butter, we're out of, whatever. They call it the 86 board. Is it 86? Wait, who ate steak? No one's waited to. Okay. It's a board that says, we're low on tortillas or whatever it is, right? So I used to always go up there and put a math problem up there, right? And there was this other guy that would, what?
I believe you.
You believe me? Okay, yeah. So sometimes it was just like not math, but just like a little quiz problem, right? Just a little like get you thinking. And there was another guy I worked with. He was the bartender, and he was an engineering major. So we always would have questions back and forth. So he came in one day with this one. It was x to the 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 x forever equals 2. Solve for x. So what number to itself, to itself, to itself, to itself, to itself forever is equal to 2 was the question, right? So it looks like this could be hard, but all you have to do here is take the log on both sides. Okay, take natural log on both sides. And then you have here x to a power. This is the power, right? You can pop that power out front. It's not to the end. This goes forever. Okay? So now what I have is this. X to the x forever times natural log of x equals natural log of 2. You buy that?
Is there notation for forever, or is that...
Dot, dot, dot.
Literally.
Yeah. Yep. It's usually 3 dots, actually. I always get a little extreme, but it's usually 3 dots. It implies forever. Okay, so here's where we are, right? But see, if I take x to the x forever, right? Shouldn't that be equal to 2? Because having one more x, see, it's like I popped all these x's off. I have one more x here, but if it goes forever, it's the same thing, right? I have an infinite number of x's. So this is just 2, right? This is just 2. So this really is 2 natural log x equals natural log 2. And then what I can do is I can divide both sides by, well, there's different ways to do this. Yeah, let me do it this way. I'm going to divide both sides by 2. Is that okay with you? Divided both sides by 2. Are y'all all right with me putting a 2 here? Yeah? Okay, divide both sides by 2, so now I have a half in front of this log, right? And now what I'm going to do is I'm going to use the property of logs backwards. I'm going to force this back up here. So I get natural log of 2 to the half power, right?